Kubernetes is increasingly being adopted in many enterprises to host containerized services and applications. Applications often need secrets such as API keys, database credentials, secure shell or SSH keys, certificates, etc. Many organizations have been hard-coded within the source code in plain text, littered throughout configuration files and configuration management tools. There's a growing need for organizations to centralize the storage, provisioning, auditing, rotation, and management of secrets to control access to secrets and prevent them from leaking and compromising the organization. This is where Vault comes in as the most widely adopted secret management system. Kubernetes has a native secret object, and today in this talk, we will learn how we can sync Vault secrets to Kubernetes secrets. Hello and welcome to HashiCorp Secure 2023. I am Pratik Khasnabis, a Senior Solutions Architect Specialist at HashiCorp. I am based in Brisbane, the capital of the sunny Queensland state of Australia. In today's talk, I will go through providing secrets to Kubernetes apps, the challenge with Kubernetes secrets. I'll then introduce the Vault Secrets Operator. Then I'll do some demo with syncing a static secret and a dynamic secret, and then have a short recap at the end. Before I go further, let's just quickly look at what is HashiCorp Vault. So HashiCorp Vault is an identity-based secret management system. It manages various kinds of secrets such as key value secrets, dynamic database credentials, PKI certificates, etc. For accessing the secret, an application or a machine or a human user would need to identify with Vault from the identity of a authentication method. There are multiple authentication methods but Vault supports, but in this talk, we are interested in the Kubernetes auth method that is used by service accounts in Kubernetes. The authorization of an authenticated entity to a secret is done through policies. That's just a very high-level view of Vault, but will help in understanding the rest of the talk. Why is it important to provide secrets to apps deployed in Kubernetes in a safe manner? Secrets should never be hard-coded into apps or into deployment manifests. It should be provided externally through some config. Applications expect secrets to be either exported as environment variables or written to a file that the application read and start up. Now, it is tempting to use Kubernetes secrets for this. After all, they are meant for storing sensitive information, right? Well, let's look at this. Secret management has multiple design considerations. It is not just that the application can read a secret. There are various design aspects to it. For example, secret projections. Applications require secrets to be presented in a specific way. Some requires at startup, some requires in environment variable, some can read a file. The scope of the secret, is it just one Kubernetes cluster? Is it multiple clusters, a data center, or public cloud? Is your workload running only on Kubernetes, or are the serverless or in VMs even? The definition of the secret, the lifecycle management of the secret, how they're created, updated, rotated, deleted, those things come into picture. Governance aspects. So who has got access to what secrets? The very important part of secret updates and rotation. Secrets should not be long-lived. They have to be time-scoped and automatically rotated. Can Kubernetes secrets do them? Caching of secrets. Sometimes in certain environments, we need to cache the secrets because the network connectivity may be ephemeral or not always there. And finally, auditability. Keeping a secret access audit log that details all secret access information is critical to ensure traceability of secret access events. The challenge with Kubernetes secrets. Kubernetes is not a secrets management solution. It doesn't provide any solution to those design considerations from the previous slide. Now, it does natively support the management and distribution of secrets, but within a single cluster only. The secrets can be loaded as an environment variable in pods or can be mounted as volumes for applications to consume the secrets. They're typically created during the deployment of an application and presented to pods only during pod creation, and the value remains unchanged throughout the lifecycle of the pod. Kubernetes does not support secret rotation. This is risky. The secrets can get stale, outdated, or expired, and that can require additional workflows to update and rotate the secrets, and then redeploy the application to consume the new version of the secret. This can add complexity and become quite time consuming. Kubernetes secrets are also only base 64 encoded, but they are not encrypted by default. And this greatly increases the risk of secret exposure especially for long-lived secrets. How Vault can solve this secret management problem? Vault, on the other hand, provides a complete solution for secret management. Vault is identity-based and only allows secret access through policies. It takes care of complete secret lifecycle for dynamic secrets, such as DB credentials. It creates temporary DB users and revokes when the TTL expires, thereby limiting impact of any secret exposure. Today, we support presenting Vault secrets into a pod as shared volume-backed config files via the Vault agent injector, which injects a sidecar container. Whilst it has sophisticated feature, it does have some resource consumption implication at scale. And that is because every pod needs an additional sidecar container. There is a need for seamless secret management for apps deployed on Kubernetes. HashiCorp recognized this, and thus we're introducing the new Vault Secrets Operator for Kubernetes. It is a first-class Kubernetes operator along the set of custom resource definitions that is responsible for synchronizing Vault secrets to Kubernetes secrets. The operator will be able to synchronize static, dynamic, and PKI-based secrets from one or more Vault server instances. The operator will be responsible for secret rotation and will provide controllers for handling the various secret-specific custom resources. The operator will also be able to perform post-rotation actions, like notifying an application directly via registered HTTP endpoint or by triggering a rolling update of a deployment. The Vault Secrets Operator is based on the Kubernetes operator pattern. Kubernetes defines operator as follows. Operators are software extensions that use custom resources to manage applications and their components. Kubernetes operators are controllers for packaging, managing, and deploying applications on Kubernetes. In order to do these things, the operator uses custom resources that define a desired configuration state of a specific application through custom resource definitions. The operator's role is to reconcile the actual state of the application with the state desired by the CRD, using a control loop in which it can automatically scale, update, or restart the application. Ultimately, operators are actually programs that run in the cluster and interact with Kubernetes APIs to automate more complex functions than those natively handled by Kubernetes itself. As you can see in this diagram, a user or a CD pipeline modifies a custom resource. The operators are watching on that custom resource. When a change event happens, operators will adjust the state by calling the Kubernetes API. In this case, it might be syncing a secret from Vault to a native Kubernetes secret object. This is the architecture of the demo. You can see in the Kubernetes cluster, there are few namespaces there. Now, the Postgres namespace is just for installing the PostgreSQL database. For the demo, this can be completely outside the cluster. And I've also installed or deployed Vault in the Vault namespace. Again, this can be outside the cluster. For the simplicity of the demo, they're both included in the same cluster. The interesting thing is the operator namespace. This is where some of the custom resources for Vault connection and Vault auth is deployed. And this is where the Vault Secrets Operator runs. The other namespace is the application namespace. This is where my sample Node.js application has been deployed into a pod, along with two custom resources, one that represents a Vault static secret, and another one which represents a Vault dynamic secrets. The Vault authentication configuration can be applied from the Vault auth custom resource. The secret custom resource includes a reference to a Vault auth. The Vault auth resource provides the parameters necessary to authenticate to Vault and perform the sync. The necessary Vault login credentials will come from service account configured in the custom resources namespace. The operators require both read and create access to any service account configured in the related Vault auth custom resource. The create permission is required to create short-lived service account tokens. The operator will periodically synchronize the Vault secret based on the configuration provided in the secret custom resource in the case of static secrets, or based on some TTL in the case of dynamic secrets. The operator may also check for drift between the Kubernetes secret and Vault. The operator supports triggering a secret rotation event whenever a Vault secret is near expiry. This operation would most commonly be done from TLS certificates managed by the PKI engine or credentials from one of the database secrets engine. In the case of dynamic secrets, the operator will ensure the secret is synced just before Vault has rotated it. After rotation sync has completed, optionally, post-sync actions would be executed. In the case of PKI resources, the previous certificate would be revoked. We can also trigger a rollout of a deployment after the rotation of a dynamic credential. Let's look at the custom resources. The first one is Vault connection. This provides the configuration necessary for the operator to connect to a single Vault server instance. Vault auth. This provides the configuration necessary for the operator to authenticate to a single Vault server instance as specified in a Vault connection custom resource. There are also custom resources that are for the Vault secrets. Vault static secret. This provides the configuration necessary for the operator to synchronize a single Vault static secret to a single Kubernetes secret. We support key value secrets, both version 1 and 2. Vault dynamic secret. This provides the configuration necessary for the operator to synchronize a single Vault dynamic secret again to a single Kubernetes secret, and we support databases, AWS, Azure, and GCP dynamic credentials. Vault PKI secret. This provides the configuration necessary for the operator to synchronize a single Vault PKI secret to a single Kubernetes secret. This supports the PKI secret engine. The flow of a secret creation looks like this. A secret custom resource is created. The event will be captured by the secrets operator. This will read the secret for the path in the custom resource from Vault. It will get the secret response from Vault. Then it will create the secret as a Kubernetes object using Kubernetes API. And then you'll get the response back from Kubernetes secret API. You'll update status metadata of the custom resource, and the creation is complete. At this point, the application can load the Kubernetes secret as an environment variable or as a volume mount. The update flow is similar. The additional step is that after the status metadata of the custom resource is updated, it will execute post-sync or update actions. Without further ado, let's look at a demo of this. For the preparation of the demo, I have done certain prerequisite steps. This included creating a local Kubernetes cluster using kind or Kubernetes in Docker. I've deployed Vault in the cluster, initialized it. I've deployed a PostgreSQL database in the cluster. I've created a customer table and inserted some rows of data. I wrote a simple Node.js app that connects to a database and displays the rows from customer table. Finally, I Dockerized that application and pushed the Docker image to Docker Hub. So this is just the steps showing to enable the Kubernetes auth method and then create a role for that auth method, which is bound to the service account named default in the namespace, Kubernetes namespace app, and it has got a policy just called dev. The audience is Vault, and the token would be valid for 24 hours. I've enabled the KV version 2 secret engine in the path KV-v2 and created a secret called webapp/config with 2 keys, username and password, with the values as shown. I've also configured a database secret engine with the PostgreSQL database plugin, connecting to the local PostgreSQL database in the cluster. I created a role for that database secret engine, which basically gives access to all tables in the schema, and the default TTL is 3 minutes. So after 3 minutes, Vault should revoke the credentials unless renewed. I created a Vault policy that gives access to the KV-v2 path and the database creds/dev-postgres path. Read access only. Let's just now do the demo. The first step is to deploy the Vault Secrets Operator. So this operator is available as a Helm chart, and I have provided some override values to the chart. Let's look at the override values. So this gives some parameters for the 2 custom resources, Vault connection and the auth method, Vault auth. So we are enabling the Vault connection and giving the address to the Vault cluster, which is just local in the Kubernetes. cluster, and I'm skipping TLS verify for the demo. For the Vault auth, I have to provide the namespace of the application where we'll deploy the secret custom resources, the authentication method with Vault, which is today Kubernetes, but in future will support other auth methods, and the mount path for that auth method. And for Kubernetes authentication method, what is the role for that auth method we're interested in, the service account of the app namespace that will be used to authenticate to Kubernetes, and the value in the audiences that is expected for this particular role. So now let's deploy the Vault Secrets Operator. So that's just running this script, this command, sorry, with Helm. So now that the operator is deployed, we have to deploy those custom resources for our application secrets. We should create a namespace named app. I've already created that one. The next step is to deploy a custom resource that represents the static secret. So let's look at the static secret.yaml file for that custom resource. So this custom resource is Vault static secret. The namespace of this custom resource is app. This is just the name of that custom resource. It is of type KV-v2, and this is the mount path in Vault for the secret engine. The name of the secret that we want to sync. So this is web app/config. And then finally, the destination, which is the Kubernetes secret object where we want to sync the Vault secret. In this case, the name of the Kubernetes secret object is secret-kv, and it will be created if it doesn't exist. Finally, there's a static secret refresh interval. This is a unique feature to this operator. It can also refresh static secret if they are changed in Vault. Before I run this on, let's just look at existing secrets, if any, in the namespace app. As you can see, there are no secrets in the app namespace. Let's also look at any pods in the namespace. And there are no pods in the app's namespace as well. I'm going to deploy this custom resource now. So this custom resource has been deployed. Let's look at the secret. Okay, so a secret called secret-kv has been created. Let's look at the content of the secret. As you can see, the secret is base 64 encoded. It is not encrypted, but encoded. So this is the password. It is the username and the password in the base 64 encoding. Let's decode them and read them. So right now it is static user 3 for the username and static password 3 for the password. Does this match or sync with the value in Vault? Let's look at that. So I'm running Vault UI here by port forwarding my Vault on this local laptop. And let's just look at the secret value. So as you can see, they're exactly matching what's in Vault. So the Vault secrets has now synced to the Kubernetes secrets. Let's go back to the demo. How about we rotate the secrets? So I'll update the value of the secret from Vault CLI. So I've got a shell inside my Vault pod where I can execute the CLI. So I'm just updating the secrets. At this point, it is updated. Let's look at the value here again. So you can see it has updated in Vault. How about the Kubernetes object, secret object? Let's run this again. As you can see, the Kubernetes secret has also been updated. So Vault secret operator is keeping your Vault secret and Kubernetes secret in sync. Let's look at the demo for dynamic database secret now. For this, I have to create another custom resource. That resource is represented in this YAML manifest. It is of kind Vault dynamic secret. Again, it will be in the app namespace, the name of the secret, the mount path. This is where it is, the secret engine is mounted in Vault database, the role for the database secret engine, and finally, again, the destination. this will create a new secret called secret-db, which doesn't exist yet. Let's run this one. So this should have created a new secret called secret-db, and it has. Let's read the content of the secret. Again, as you can see, it will be base 64 encoded, but the data is there. There's a username and a password. Let's look at what happened inside Vault. So inside Vault, if we go to leases, we will see that a lease has been created for that dynamic database credential that was just generated from Vault. And it will expire in 2 minutes because remember the TTL we set is only 3 minutes. So only 1 minute remains for this credential. Let me now deploy my application. The application is very simple. It's just a Node.js application that connects to a Postgres database engine and then fetches the data from customer table and displays in the table. I also show the connection string for information. Obviously, it should not be done in a real production application. The critical thing is that it is reading the database user and database password from the environment variable or the environment in the process. How can I supply these environments to the application? First, let me show that one. So I have created a Docker image for this application, and I've got a Kubernetes deployment manifest for the application. So the important thing is that the container is my Docker image, but I'm providing these environment variables like DB password. Where is it getting the DB password from? It is getting from a reference to a Kubernetes secret. The name of the secret is secret DB and the key is password. Same for the DB user. The name of the secret is secret DB and the key is username. So Kubernetes objects can be natively referenced as environment variables within the pod specification or the container specification. You can also mount the secret in a volume as well. So there's the volume mount, and the volume secrets is mapped to the secret/db Kubernetes secret object. Let's create the app now. So I created the app. And I've also got a service for that app because it is listening on port 3000. So the service has been created. And let me port forward this one to my machine. So I'm port forwarding from the service port 3000 on my machine. And let's look at the application. So as you can see, the application is using this temporary database credential, username, and password that was created and obtained from Vault and using the Postgres, local Postgres engine in the cluster. And it is retrieving the secrets from the database. If we look at Vault, and let's just go back, we'll probably see a new secret has been, the secret has been renewed because it was nearing its TTL expiry. So what you can see here is now in the demo that Vault is keeping the database credential the operator is keeping the database credential in sync with a Kubernetes secret object. And that's why it is a very simple and seamless secret management in Kubernetes. Let's go back to the slides quickly. So I've gone through the demos. So I've shown the demo app, how we're getting the credentials from environment variables and how the environment variables are referenced from a Kubernetes secret. So this means your applications are completely using native Kubernetes object, that they're not Vault aware. They don't need to know about Vault. It doesn't require a sidecar container injection. So your resource consumption is very low. So come to the end of the talk, and the key takeaway is that the Vault Secrets Operator is the newest method for Vault and Kubernetes integration. It implements a first-class Kubernetes operator along with a set of custom resource definitions responsible for synchronizing Vault secrets to Kubernetes secrets natively. Thank you for coming to my talk, and I hope it has been useful to you. These are some of the further resources, and the slides will be available after my talk. Thank you once again for attending HashiTalk Secure 2023.